I'm Kim Velasquez, and this is the first in a series of videos to accompany Biology 102 at Palomar College. And we start with chemistry in this course. We're going to talk about some really basic chemistry that is really important to your understanding of biological systems. We start with atoms and subatomic particles, and then we're going to work our way up to molecules in the next couple of lectures. So let's start with just a couple of really basic definitions. Start by defining matter. What is matter? Matter is anything in the universe that has mass and occupies space. So matter has mass and it occupies space. And that matter is made up of atoms. Atoms are the very tiny particles that comprise all matter on Earth. So atoms are very tiny particles that comprise matter. And really, an atom is the smallest you can break down any chemical element and still have it retain the properties of that element. So if we had one atom of carbon, it would still behave like carbon. It would still have all the chemical properties of carbon. Once you get smaller than an atom, it's not going to have all the same chemical properties as that element had. So an atom is the smallest you can get and still retain all the chemical properties of that element. But in this course, it's really important for us to understand something smaller than an atom. We need to understand subatomic particles. Again, common question, why do I need to know about subatomic particles? This is not a chemistry or a physics class, but it's very integral to your understanding of molecules and how certain molecules form. So these subatomic particles are a very important part of your understanding of biology. So we're going to learn 3 subatomic particles in this course, namely protons, neutrons, and electrons. These are the 3 that are of most importance in understanding how molecules form. So protons, neutrons, electrons. Let's look at just a basic atomic structure to see where these are located in the atom and what electric charge these subatomic particles have, because that's going to be a very important part of the story. Okay, so I'm just going to draw a very general atom, and every atom has a region at its core called the nucleus. Just as your cell has a nucleus, the atom has a region called the nucleus. And in this nucleus are 2 of the 3 subatomic particles, namely the protons, which I'll represent as a small letter P, and the neutrons, which I'll represent with a small letter N. So protons and neutrons are located here in the nucleus. And then these electrons, small letter E, they are not in the nucleus. They are actually orbiting outside the nucleus. Electrons. So in the core we have the protons and neutrons in the area called the nucleus, and then orbiting out here we have electrons. There is quite a distance here. An analogy that's common in textbooks is if you picture the nucleus being a pencil eraser on the 50-yard line of a stadium, and the electrons being gnats orbiting the stadium, that would kind of be the relative distance and size of that atom. Obviously we can't draw that distance on the board, but really picture that nucleus being very small and very dense. This is where all the weight that we're going to consider in this course, all the weight of the atom, it comes from the nucleus. The electrons don't weigh a whole lot. They don't contribute significantly to the weight of the atom. So when we talk about atomic weight, we're going to be talking about the protons and the neutrons and how much they weigh. So protons, neutrons, electrons. Protons, pro means positive. Protons actually have a positive electrical charge. So here in the nucleus, protons have a positive charge. Neutrons have no charge. And electrons have a negative charge. Why does that matter? It matters because electrons are going to be a very important part of some really critical processes that happen in living systems. So it's really important to understand electrons. But it's also important to understand just some basic electric force principles, one of which is the principle that opposites attract. opposite charges attract each other. Okay, so the positive and negative charges in this atom are going to be attracted to each other. And really, all matter on Earth and in the universe is held together by this electric force, by the positive charge of the proton attracting the negative charge of the electrons. Another important concept to understand is that like charges repel. So if we had more than one proton in this nucleus, a plus and a plus, those would tend to repel each other. Let me show you a slide. Just skip forward here. So plus and plus would repel each other. Minus and minus would repel each other. But opposite charges, unlike charges, attract. So if we had two positive charges in the nucleus, they would tend to repel each other and the whole atom would fall apart. That's the role of the neutrons. The neutrons are going to separate those two positive charges and hold that atom together. So let's skip forward here. Let's look at a helium atom. We're going to talk in more detail about the periodic table, but this is helium. Okay, and helium has 2 protons and 2 neutrons in its nucleus, and then it has 2 electrons orbiting out here. So this is just the general structure, really, of any atom, but more specifically helium. 2 positive charges, they don't repel each other thanks to these 2 neutrons, and then 2 negative electrons orbiting that nucleus. So that nucleus has a positive charge, it's attracting those negative electrons. Now let's look more specifically at this periodic table of elements. It's important for you to have a paper copy of this, print it out from the internet, look at a textbook. It's important for you to have a copy of the periodic table because it's hard to see the detail on the screen. And I would also like for you to write on that periodic table. Okay, so you notice there's a little rectangle that shows carbon, and I'm going to draw that same example on the board as we go through this. But before I do that, you probably noticed a couple of things about this periodic table. One, that it's arranged in columns and rows, and the chemicals, the elements that are in each column have something in common, and each row have something in common. So they're purposely arranged that way. Sorry, I have this little tickle in my throat today. You'll also notice that this number in the upper left-hand corner, called the atomic number, increases as we move up the periodic table, starting at 1 with hydrogen, 2 helium, 3 lithium, just keeps going. Okay, and then this number on the bottom, the atomic weight, that keeps increasing too as we go along the periodic table. Most of what we're going to be concerned with in this course occurs in this column, and then we skip over this, and this. And those columns you can actually imagine with a Roman numeral over them. This first would be column 1, and we would represent that with a Roman numeral 1. So if you have a periodic table, please write a Roman numeral 1 over that first column. That would be the one with hydrogen, lithium, sodium, etc. Okay, and then the one next to that would be column 2. So beryllium, magnesium, etc. Okay, then we're going to skip all the way over. Column 3 is going to be this one with boron, aluminum. Okay, and then 4 is going to be the one with carbon. Okay, and then 5, the one with nitrogen. 6 with oxygen. 7 with fluorine. Okay, and then finally column 8 is going to be that very last one with helium, neon, etc. Okay, so we're mostly going to concern ourselves with those 8 columns as we go through the story. Okay, so going back to that example, the rectangle with carbon. You notice the carbon is represented by what we call a chemical symbol. That chemical symbol can be either 1 letter or 2 letters. And it does represent the name of that the name of that element. It's not always how we spell the element. For example, AU is gold, and obviously that's different from G. So AU actually stands for Orion, which is the Latin name for gold. So it's not always the English name. Chemical symbol, you should start to recognize the chemical symbols for some of the common elements. And then obviously, chemical name, or the name of that element. Okay, and then we have what's called the atomic number. And that atomic number tells us a couple of really important things about that element. It tells us the number of protons in the nucleus of that element. Okay, so how many protons does carbon have in its nucleus? We know that from the atomic number. It has 6 protons in the nucleus. And it just so happens that every element on this periodic table has an equal number of protons and electrons. So that atomic number not only equals the number of protons, it also equals the number of electrons. That's really important to realize, because what it's saying is the number of plus charges equals the number of minus charges, and atoms have no net charge. Positive equals negative charges. Okay, and then lastly, at the bottom we have the atomic weight. And the units for that are not written on the periodic table, but the units for the atomic weight are Daltons. D-A-L-T-O-N-S, Daltons. That atomic weight, as I mentioned before, this is the atom. Remember, the electrons are out here. Protons and neutrons are in the nucleus. And that's where the mass of the atom is. So this atomic weight equals the weight of the protons plus the weight of the neutrons. And guess what? Each proton weighs 1 Dalton, and each neutron weighs 1 Dalton. So it's not just the weight of them, it's the number. So it actually equals the number of protons and the number of neutrons, because each weighs 1 Dalton. So if you add them up, that's the atomic mass. So we already know the number of protons that carbon has. It has 6. So then we can look at the atomic weight and calculate the number of neutrons that carbon has by just subtracting atomic weight minus number of protons equals number of neutrons. Okay, so atomic weight of carbon is 12 minus 6. Carbon has 6 neutrons. They're not always equal though. Let's look at nickel. Nickel is atomic number 28. And atomic weight is 59. How would I calculate the number of neutrons in nickel? Well, let's start by determining how many protons nickel has. How many protons does nickel have? 28. Remember, that atomic number is the number of protons. It's also the number of electrons. This 59, the atomic weight, equals protons plus neutrons. So to calculate neutrons, we would just say 59 minus 28. Nickel has 31 neutrons. If you have any questions about this, please rewind the tape and listen to the explanation of atomic weight again. So just a couple of quick questions before we move on. How many protons are in sodium? Well, in order to figure that out, you need to look at your periodic table, and you also need to know that sodium is not S on chemical symbol. S is actually sulfur. So you should start learning the chemical symbols for some of the major elements. Na is sodium. And how will you tell how many protons sodium has? You will look at the atomic number. Sodium is atomic number 11. So that means it has 11 protons. How many electrons are in calcium? Again, you need to know that calcium is Ca. Okay, and it's atomic number 20. Remember that 20 equals the number of protons. It also equals the number of electrons. So calcium has 20 electrons. Okay, and finally, how many neutrons are in zinc? Zinc is Zn. So let's go back to the periodic table. Sorry, I have to hold it down low to change it. Okay, zinc is atomic number 30. Atomic mass is 65. So how are we going to tell the number of protons? 30. How will we calculate the number of neutrons? 65 minus 30. Zinc has 35 neutrons. Get back to the question, sorry. 35. If you have questions about any of those questions, please rewind the video and watch that part again. In the next video, we'll move on and start talking more specifically about electrons and where those electrons are situated and how many each atom has is going to determine the chemical behavior of each atom. Hi, we're going to continue talking about subatomic particles and now talk more specifically about electrons. I'm going to start by writing a statement on the board, and then as I go through this lecture, I will explain what this statement means. Okay, so the statement goes like this. The number of electrons in the outer electron shell. So this is obviously something I'm going to have to define for you. It's the number of electrons in the outer electron shell that determines the chemical behavior of an atom. So determines chemical behavior of an atom. Chemical behavior. That's a big deal. We need to understand how certain atoms behave chemically, who they bond with, or if they don't bond with anyone, and why, and what kind of bonds they typically form with other atoms. That's very important for understanding the molecules that make up living systems. So the number of electrons in the outer electron shell determines the chemical behavior of an atom. What does that mean? Well, let's start by going all the way back to the periodic table. And let's look at the electron configuration for hydrogen. Electron configuration is a term which really is just asking, where are the electrons located for that atom? And in order to understand that, you have to know something about electron shells. Okay, so let's start with hydrogen as our example, and hopefully we'll go through a couple of examples and then we can better define this statement. Okay, so hydrogen is atomic number 1. That means it has 1 proton, but we're talking about electrons, so more importantly, it has 1 electron. This is hydrogen's nucleus with its 1 proton, and that 1 electron is going to be located in what is called the first electron shell. The first electron shell is the one closest to the nucleus, and that first electron shell can hold a maximum of 2 electrons. So it has 2 spots available, so it holds a max of 2 electrons. 2 spots available. Well, hydrogen has 1, so that 1 is going to be located in that first electron shell. That means hydrogen has 1 spot still available to be filled. If we move up the periodic table to the next element, helium, all the way over here in the last column. Helium is atomic number 2. I'm going to cheat and not erase. Helium, atomic number 2. That means it has 2 electrons. 1, 2. So helium doesn't have any spots available. Now moving to lithium, atomic number 3. 1, 2. We're out of room in the first electron shell. So that next electron is going to have to go to what we call the second electron shell. And that second electron shell can hold a maximum of 8 electrons. So second electron shell holds a max of 8 electrons. Okay, so 8 spots available. 1, 2, 3, 4, 5, 6, 7, 8. I'm drawing them this way to create a pattern that will follow as we start drawing molecules. It's just an easier way to depict this on the board. It's really not reality. It's just an easier way to draw it. Okay, so lithium has 3, 1, 2. That means lithium has 1 electron in that outer shell. Okay, let's skip forward all the way across that row and go to neon, atomic number 10. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Neon has filled that whole shell. If we go on to sodium, atomic number 11, we're going to have to add a third electron shell. And that third electron shell, for the purposes of this course, we will assume that that third electron shell also holds a maximum of 8. So third electron shell holds a max of 8 electrons. I just realized I should say holds. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. And sodium is just going to have 1 out here. Okay, so let's go back to our statement here. The number of electrons in the outer electron shell determines the chemical behavior of an atom. The outer electron shell is going to be the last shell that actually has an electron or more in it. So if you have one or more electrons in that shell, that is your outer electron shell. So for sodium, how many electrons does sodium have in its outer electron shell? It has 1. Another term for that outer electron shell is valence shell. Those terms are used interchangeably. Valence shell means the same thing as outer electron shell. And the electrons in that shell are called the valence electrons. So stating that previous question just another way, I could ask, how many valence electrons does sodium have? And the answer would still be 1. Sodium has 1 valence electron, has 1 electron in its outer shell. That is going to be significant in determining the chemical behavior of sodium. Every element wants or needs to have a full outer shell in order to be stable. So let's add something new to this important statement. Every atom needs a full outer shell, also called the valence shell, to become stable. If an atom does not already have a full outer shell, it is going to do something to fill that outer shell. And that's going to be the basis for chemical bonding. If you already have a full outer shell, you don't need to do anything. So, going back to neon, atomic number 10, remember this was the outer shell for neon, atomic number 10. Guess what? Neon already has a full outer shell. So neon is actually non-reactive. It doesn't react, it doesn't bond with anyone. It already has a full outer shell. It doesn't need to do anything else to fill that shell. So, elements with a full outer shell, more specifically I want to say atoms with a full outer shell, are non-reactive. The other term we can use for that is inert. If something's inert, it means it doesn't react. And as it turns out, the elements in this last column have a full outer shell, and therefore they don't react. They're inert. The other columns are going to react. And remember, we talked about, let's skip way ahead here. We talked about putting column numbers over the first 8 columns, skipping this middle part. So column 1, 2, 3, 4, 5, 6, 7, 8. Well, guess what? There's a shortcut. For the purposes of this course, there's a shortcut to figuring out how many valence electrons an element has, how many electrons are in that outer shell. If you're in column 1, you have 1 electron in your outer shell. Remember, we did hydrogen, lithium, and sodium, and they each just had 1 in their outer shell. Column 2, 2 electrons in the outer shell. 3 has 3, 4 has 4, all the way over to column 8. Column 8 has 8 in the outer shell. The exception, of course, is helium. Helium only has 2 total, but it does have a full outer shell. So everything in column 8 is inert. Everything in column 8 is perfectly happy being by itself. In fact, it cannot bond with any other atom. Those atoms all exist in the universe just by themselves. They don't need anyone else. They are full. Their hearts are full. They don't need anything else. Their outer shell is full. They are perfectly happy, non-reactive, stable. But anything that doesn't have a full outer shell, so everything in columns 1 through 7, is going to do something to fill that shell. So if we look at the electron configurations, again that's telling us where are the electrons located for all of these elements, you can see this is column 1, and they each have 1 in their outer shell. Okay, this is skipping all the way over. I don't know why they skipped column 2 here, or 3. Okay, so this is column 4, carbon. 1, 2, 3, 4. Phosphorus, column 5. 1, 2, 3, 4, 5, and so on. And then if we get all the way over here, column 8, neon, 1, 2, 3, 4, 5, 6, 7, 8. So again, shortcut is the column numbers. Or you can sketch the electron configuration and determine that yourself. Sometimes you will be asked in this class to sketch the electron configuration. So you do need to know how to do that. You need to know how to do this. If I asked you to draw the electron configuration for neon, okay, so this is neon. If I asked you to draw the electron configuration for neon, this is how you would draw it. If I asked you how many valence electrons does neon have, you could either sketch it and count, or you could do the shortcut. Then column 8 has 8 electrons in its outer shell. Okay, again, if an atom does not have a full outer shell, it's going to be reactive. It's going to do something to fill that outer shell. And we'll talk about that in the next lecture, and we'll start seeing how molecules form.